So regarding submitting your homework, I noticed some of you guys just take a picture, sometimes like this way, sometimes this way, and post the homework same way. And I don't think, considering you guys will become engineers working in firms and companies, you may need to develop a certain level of professionalism. When you scan something like in a portrait mode, it has to be posted on portrait mode. For you guys, just rotating the picture, it takes 5 seconds, but I cannot rotate that picture in Blackboard to read it. Even if I can, I don't think it's the best representation of you, because remember, you are represented by your work, right? People don't look at your clothing or name or how you look, don't matter, right? Those don't matter. It's just as an engineer, you're represented by your work. And I think it's a good idea to start developing some, level of professionalism. When you scan stuff, make sure it's like, if you write it in a portrait mode in your paper, it has to be shown same way, because it's hard to read it when it's lateral. The other thing is, I noticed some of you guys, I think, take a picture. There are different apps for scanning that when you take a picture with those apps, they clean the background. If it's, that the paper looks kind of brownish or sometimes yellowish, they make this white, and then you can take like 5, 6, 7, 10 pictures back to back to back and turn all of them to a single PDF that you can email it to yourself or whatever, right? Please use one of those. I'm going to put in the chat the one I use. If I think it's called Scan or Cam Scanner. I'm going to put it in the app. Right. And I'm sure there are others. I found this some years back, and I found it interesting because, it cleans. Even if you take a picture little this way or that way, or it's like a trapezoid shape, it finds the corners, make it like a rectangle, makes it nice. You can make those adjustments, but the way that it cleans the background and make it like a white background is more visible, because some of the things you post, I really cannot read. For one student, I asked him to resubmit because I really couldn't read anything. And when you write with pencil, please make sure it's a little harder that, it's readable, right? And I have seen still some, irregularities in your homework. It looked much better compared to last time. But please make sure you spend time solving the problems yourself. It's okay to work with friends, but to discuss the concepts. But when you understand how it's done, I think it's critical to do it yourself. And now that the third homework was kind of short version of the previous ones, fewer problems, I think that could take care of your time stuff. With that intro, any question? And one more thing, I have seen the second quiz grade wasn't as good as first one. Some of you guys seem to be maybe lost or something. I put some notes when you graded your homework. I know you guys spend time and, study and everything. And I know from the history that when I say you need to do more, it looks offensive that I don't recognize your hard work. That's not the case. If you spend 5 hours, I'm just giving numbers, right? If you spend 5 hours to do something, whatever, if it's a sport, if it's art, if it's your homework, and your outcome is not as good as you expect, there are two cases. Either 5 hours is not enough, or you have to improve your efficiency or your concentration and all of that, right? So whatever time you spend, if your quiz goes like 4 out of 10, 3 out of 10, even 5 out of 10, single problem from single chapter that you know what's going on, right? It shows you have not reached the depth of the concepts. You need to practice more. You need to understand the concepts. If you need help with any part of the course, please let me know. I'm available. I mean, I'm busy, but I can make availability for you guys certain times that works for you and me to meet and discuss some of the concepts that you may struggle, if it's problem solving or if it's the basic concepts of the lecture. Okay, we are almost done with half of the course by end of today. We finish particles and you're going to have a midterm next Monday, July 3rd. So you have 1 week to review your stuff, because based on my experience and as I see the way some of you perform, not submitting bonus problems, not submitting even the main homework, it is likely that you fail if you go with this trajectory. Okay, and this is the last thing I want to see, that students come and register for summer course and fail, and it may keep you 1 semester behind others, right? Because I think dynamics is a critical course. You have to pass it to go to upper division, and also is a prerequisite for multiple courses, so you have to be careful. Okay, now with that note, any question or comment about the course? We're good, or you don't care? One of the two, right? I don't know. Okay, let's continue with the course stuff. I am going to share the screen. So we talked about principle of impulse and momentum. Let me just review the equations. The equation was this: initial and final linear momentum of the system, they are related to the external impulses applied. So technically, the change of impulse, the momentum of the system is the result of external impulses. That was the principle of impulse and momentum. And then we said, if there's no external impulse, either there's no force or the forces are internal, they balance each other, action, reaction things, then it makes conservation of linear momentum. We gave different examples, from walking on a boat to explosion of fireworks or any explosive, and some other examples, right? Even collision of the cars, that when you have those strong forces, those are all internal, action, reaction, they cancel out each other. And also remember that when something like very sudden impact accident happens, this collision happens, the time is very small. So for ordinary, let's just call it ordinary forces like gravity or things like that, because that delta t is very small, integration of f dt is negligible. That's why in fireworks, when explosion happens, we neglect the force of gravity, because those explosive forces could be 50, 100 times more than gravity, and the effect of gravity is technically negligible. Same thing with collision. If you consider the friction force between the tires and the ground, which is in terms of few thousand Newton, right? If you consider with the force that is created between the two cars during the collision, which is possibly tens, maybe 100,000s of Newtons or pounds, you can neglect those. And that's why you can get initial linear momentum will be the same as final linear momentum. And this is for single particle. This is for a system of particles. This is very useful to solve certain type of problems as we talk right now. Impact. So impact is the collision between two particles with a certain, conditions. One is you have relatively large contact forces between the two particles, like, again, collision of two cars, like when you play tennis and hit the tennis ball with the racket. when you play, I don't know, soccer and, you know, kick the ball. If you shot a bullet to a block of wood, the force is very large in all of these cases. Even when you play basketball and hit the ball to the ground, the force is relatively large, much larger than the weight of the basketball. And the other thing is, in all of these things, the whole thing happens in a very short period of time. If you want to see how the basketball hit the ground and bounces back, you probably need high-speed cameras to get a slow motion, because it happens maybe in like 1/100th of a second or less. Same thing with collision of the two cars, same thing. Here's the thing. If you push your hand, I usually show this in the class, if you push your fist, I don't know if you can see my hand, if you push your fist to the wall, no matter how strong you push it, it's not hurt as much. But as soon as you punch the wall, it hurts much more. Why? Because it's kind of impact large forces in very short period of time. So these are examples of impact. And to analyze impact, we can use the equations we develop in this content and see how we can solve them. Let's see some examples. I'm not sure how good it's going to show it to you on so this is high speed camera, you know. Let me see. I'm going to highlight this. I know this is Zoom, you cannot see it perfectly, but I'm going to pause the video. First of all, anyone here plays golf by any chance? Kelly, you play golf? Okay, so I mean, those I never played. I probably can't even hit the ball with the club or anything. But if you touch the golf ball, it's really, really hard, right? It's almost like a rock hard. It's not like tennis balls or maybe even like some other. I was at the field a few days ago. People played a practice field hockey. It's a rubbery ball. It's very hard, but it's still. I think tennis. The golf ball is harder. Now, considering how hard the ball is, the video you see here may surprise you. You see how much deformation? This is almost the beginning of the contact. You know, is very close. And look at here. It's almost like more than 1/4 inch deformation in the ball. Why? Because the force is so large that deforms the ball easily, and then goes to the maximum deformation here, and the ball gets away from the club surface and gets back to the original form. And right here, it separates. So technically, if you analyze this motion, before contact and after contact, nothing happens, right? During the contact, this is where you get deformations increase to the maximum. Then deformations decrease to minimum, which is 0. The ball gets to the original shape and moves on. Because this is very hard object, creating such a large deformation requires very large force, and that's what you do with the club, right? And that's why this tiny ball could travel 2, 3. How much is the maximum usually they kick the ball? How far it goes? Like 200 yards is normal, right, Kelly?
Yeah, I would say 200 yards is pretty normal. I think some people could hit a little farther than that too.
So you can see how large the force should be to hit this and makes it go like 200 yards. You cannot throw it by hand and going that far. I don't think you can throw it, like just throw it by hand, like the way we throw like softball or things, or like people in baseball. It probably doesn't go in 100 yards, right? no matter how strong. So this shows how big the impact forces are. Any question about this concept? So I think this example shows what we talk about when we talk about impact. The contact times is like millisecond, maybe less, few milliseconds and things like that. The forces are extremely large. I suggest you guys, if you have a chance, go get a golf ball. If you don't want to buy it, I think you can find it in Walmart something. Just try to squeeze it and see how hard it is to make tiniest deformation. That shows how large the impact force is. Now, these two characteristics, when they happen, they create impact, right? Now, when it comes to analyzing impact in terms of the geometry of the impact, we divide it into two categories: direct central impact and oblique central impact. Direct means they come face to face. So the line of impact and the velocities are the same. And you have a plane of impact when the deformations happen, which is perpendicular to the line of impact. This is for direct impact. It's like two cars coming head to head. I remember one of the Fast and Furious movies. At the end, the two cars came just hit face to face. That is like direct impact. The two cars have this velocity in the same direction, and that is the line of impact. The second one that you see here is oblique impact. As you see, the line of impact is where the center of the two objects, now it's kind of a sphere here, are connected. The velocities have some angle. So they come from the side. This is like when two cars collide at an intersection. One comes from one lane, one comes from the other perpendicular lane, hit each other. So there's some angle between the velocities and the line of impact. This is easier to analyze. You start with this guy, and then we extend the concept to this guy. So any question about the concept of impact? Is it obvious for everyone? Right? So when you kick the soccer ball is softer. You possibly can see the formations. And I suggest you guys go, Google some of these videos and see how large the forces are. There are nice videos in YouTube and on internet that you can find talking about this impulsive forces. Let's call them impulsive forces because it happens at a very small period of time. Now, when we talk about direct impact, as I said, we have multiple stages. Before impact, nothing happens. And remember, if the two objects move on the same line in the same direction, V1 has to be greater than V2 to have an impact. Otherwise, the mass 2 is going to get away from this guy. So if this goes faster, eventually they hit each other. Let me do this in the tablet because I want to give a little more details here. And then we come back here and discuss this. So if you consider the direct impact, as we saw in that first part of the slide, the two balls or the two objects come, this is V1, this is V2, object 1, object 2, they both go this way. At some moment, object 1 just touches object 2, right? This is where they just come to contact. From here, because one goes faster, it's going to push the object 2. And then we're going to go to the point that, and I'm going to do this a little larger, the object 1 is deformed the object 2 is deformed in the maximum deformation. So here, still V1 is bigger than V2. It's not the same value, let's call it prime, right? Or let's not call it prime because we use the prime later. But the velocity of object 1 is still faster than object 2. When they have the maximum deformation, at the maximum deformation, at that particular moment, there is no relative velocity between 1 and 2, right? Because 1, I don't know if you can see my hands, 1 deforms 2, and when there is maximum deformation, at that moment, both of them have the same velocity. So let's call this velocity as V0 or something, which is for both. Then 2 is going to go faster than 1 because it's going to get away. 1 has given some force to 2. And then V2 prime is bigger than V1 prime until they come to the barely contact point, and then they're separated. So technically, when they are not in contact, they are independent objects or particles moving around. The impact happens here, right? As soon as they start contacting each other, there's going to be some force, and I'm going to draw the force versus time here because we want to calculate the impulse, right? If this is force and this is the contact time, let's say this is when t equals to 0, right at this moment, when the two come just into contact, right? What happens after that? 1 is going to keep pushing 2 and creates the formation, similar to what you saw in that video, right? The club pushes the golf ball and the deformation increases. What means when you have larger deformation? Larger forces, right? So the bigger the force, the bigger the deformation. So technically, if this is the beginning of the contact, this red dot, as the contact develops and these two are deformed, the force kind of goes up to certain way. It's not going to be linear, whatever the shape is, because the deformations are not linear, but whatever it is, until it reaches a maximum force where you have the maximum deformation. Right? Let's call this point as T0. So T equals 0, no force. The forces start increasing until this point that deformations are maximum. At that maximum point, the two objects have the same velocity. Now, after that, as soon as object 2 starts getting away from object 1, what happens? The deformations decrease, right? You saw it in the video too. The golf ball gets to the maximum deformation, that kind of restores its shape. And as it restores its shape, it means the forces are getting smaller and smaller until they barely touch and the forces are 0 and they're separated. So technically, the contact forces increases, reaches the maximum, and then decreases. If you want to calculate the impulse of that force, impulse is going to be integration of F dt, right? And integration of Ft from 0 to T0 or from 0 to T halfway or all the way, doesn't matter, right? Then that is going to be this area. This area under the curve is going to be your impulse. Any question about the physics of the impact and how the forces work? Is it clear? So remember, beginning of the contact, maximum deformation, and end of contact. So you have one interval here, which is this guy on the curve, and one interval here, which is this part on the curve, right? We're going to create some equations to analyze this. Let me know if you're done writing. Any question? Okay, now let's go back to the slides. It's technically the same thing, but with the less graphics. That's what I showed you. So before impact, as I said, there's a point that nothing happens. Then they come to contact. Then they reach the maximum deformation during impact. And then M2 is going to go faster and they separate again. I just added the beginning and the end of the contact between these three stages, right? So, and as I said, when the maximum deformation happens, at that particular moment, the two have the same velocity. Why? Because the relative velocity between them is 0, so they should have the same velocity. Now, if you analyze this, again, this is how the forces develop. The first period or the first part, we call it deformation period. There's going to be forces acting between the two objects, action and reaction. These forces create deformation in object 1 and object 2, and this is the left side of this curve, this red curve, right? This is deformation period. Here, when you have the maximum deformation, you reach the maximum force, and after that, you're going to go to restoration period, when the two objects get away from each other and restore to their original shape, right? And that is where the forces go from maximum to 0. Any question? So I explained the physics in details, but when we develop the equations, we never come back to these concepts. But I think it's important to understand how this happens. So after this, now, this is what we talked about. The external forces that act on the two particles, there may be relatively large forces like gravity or whatever else, right? But because the time is very small, like 1/1000th of a second, 2/1000th of a second, like that, they create negligible impulse. So if we ignore the impulse of external forces, then we can use the conservation of linear momentum for the two particles together, which means if this is before impact and this is after impact, the linear momentum of the system before impact altogether is equal to the linear momentum of the system after the impact. Remember, this is a vector equation, but because this is only one direction, like a rectilinear, V1, V2, V1 prime, V2 prime, they're all in the same direction. So technically it's like you only have X component or Y component, right? This is the equation for linear momentum. Now, when there is an impact, you usually know the initial velocity for the two particles. What are the unknowns here? Aaron, what are the unknowns in this equation? We cannot hear you. I think you're muted.
Currently, it's the mass and velocity.
The unknowns. Remember, when the two particles collide, you usually know the mass. The problem could be defined in a way that they give other stuff. You have to calculate the mass. But usually, when you have two particles colliding, you have the initial velocities, you have the masses. You are looking for the velocities after the impact, right? Which means the unknowns are V1 prime and V2 prime. So technically we have two unknowns, right? With one equation. So how we're going to get the second equation?
Would you have to take derivative of the distance or the displacement?
Good observation. Remember, the impact happens at such a small time. Those displacement, you could kind of neglect it. And if you want to do it, remember, the force increase is crazy, right? It's not even constant. The acceleration is hard. So we're not going to go through acceleration, displacement, and stuff because it creates more complexity. Technically, the reason we go through this impact and momentum because we want to avoid acceleration and integration and all of that because it's really hard to imagine two cars collide and move one way. How do you get the forces? It's a very complex mechanical problem, right? So let me ask you this question. I'm not expecting you know the answer, but if I hit, imagine we're talking about two objects, right? I want to see if any two objects hit each other, is the results the same? For example, you have a tennis ball and hit it to the wall. What happens? It bounces back. Let's say the tennis ball is, I don't know, 100 grams, right? Now, if I get a dough, like a baking dough, the bread dough, 100 grams, and hit it to the wall, what happens? You guys have seen dough, right, in your life? If you hit a dough to the wall, what happens? Does it bounce back like a tennis ball?
No, it just deforms and sticks to the walls.
Sticks to the wall. Let's put it this way. You have a basketball fully inflated, right? You hit it to the ground, comes back to your hand. It could be, I don't know, 1 pound, 1.2 pound, whatever the weight is. You deflate the basketball, its mass and weight doesn't change, right? You hit it to the ground, does it bounces back the same? If you deflate the basketball, it's like half pressure or less than half. Does it come back the same? No, which means the impact does not only depends on the masses and the velocities, it also depends on the materials hitting each other, right? It's kind of like friction. Friction depends on the normal force, but also depends on the surface of the two objects in contact, right? It's not that everything is like 10 kilograms has the same friction. And it's not that everything you put on your table or your desk, because one side is desk, everything has the same friction. One side is the desk, The other side is the second object moving relatively to one another, right? Same thing here. When you play like a snowball in the winter, hit each other, what happens? You throw the snowball, it hits your body, it sticks there. Why? Because the nature of a snowball, and if you do the same thing with a tennis ball, the material properties are not the same. So to create the second equation, we have to understand the nature of the contact between the two objects. And that will create a second equation. Is the target, what we are looking for, clear? So practically, not every two objects of same mass hit each other are going to have the same results for impact. So with that being said, we need another equation. Let's see how we can find it. That physical property that depends on the behavior or the nature of the two objects is called coefficient of restitution. And this is how we define it. The impulse of the restoration divided by the impulse of the deformation. Now, we cannot define the forces instead, because for every mass for 1 and 2, excuse me, the impulses are equal to the change of momentum. For this impulse, I put the change of momentum. For this impulse, I put the change of momentum. And for particle 1, this is how E looks like. If I do the same thing for particle 2, restoration impulse divided by deformation impulse is a change of linear momentum from end of the impact to the maximum deformation here, from original contact to the maximum deformation. That's how your change of linear momentum are. And then you get that. Now you see here, I have V1, V prime 1, V2, V prime 2. I created two equations. I also have this V0, the velocity where the maximum impact or maximum deformation happens. We are not usually interested in what happens right at that moment, right? So the best way is to solve these two equations or combine them together and eliminate V0. If we do that, then you get this. The coefficient of restitution will be the relative velocity of the two objects after the impact divided by the relative velocity of the two objects before the impact. And remember, we don't have to memorize 2, 1 or 1, 2. Whatever in numerator, you switch the objects in the denominator, right? And it makes it positive. Now, if V1 is bigger than V2 before impact, this is positive. And after impact, V2 prime is bigger than V1. We go that way. This is a physical parameter that depends on the nature of the two objects and the way they touch each other, right, at the impact. Now, if you look at it, if you have a perfect elastic impact, the relative velocity before and after will be the same. If you have a perfect plastic impact, like when you hit the dough to the wall, what happens? It's going to stick to the wall, right? How much is the velocity of the wall? 0. How much is the velocity of dough that is stuck to the wall? 0. So 0 minus 0 gives you 0. So technically, if the two things stick together, the relative velocity will be 0. The coefficient of restitution is 0. If it's a perfect kind of impact, perfect elastic, I mean, perfect impact doesn't mean perfect elastic, then the relative velocity after and before is the same. Perfect elastic impact you can get, for example, if you have glass is close to perfect, if you have hardened steel balls hitting each other, like hard material, it gives you close to 1. You see steel and steel less, lead on lead, lead is a very soft material, and then perfectly plastic gives you 0. So that's how things change. Now, if do you guys have played billiard or pool, table pool? How hard are those balls? Again, really hard, right? Technically, when you play pool, it's all about impact. And I expect that the coefficient of restitution, of course, there's nothing perfect elastic. It's not 1.0, but it could be like 0.95 or 0.9, close to 1. The harder, the better, right? That's why you cannot play pool with tennis balls, because tennis balls may have coefficient of restitution of 0.67. So it hits the things that the speed goes down quickly, and you cannot run it the way that you do with the actual pool balls. Same goes with bowling ball, right? Bowling is very hard and it's heavy, and it's all about impact. A lot of sports are about impact. I think boxing is about impact because those punches create impulsive forces, right? Very large forces. Any question? So technically, this is the second equation you need to solve a problem. 2 equations to unknown. Remember, E is kind of a physical property. You have to experimentally determine it, right? Similar to friction coefficient, when you solve a problem, usually E is given. Or if someone asks to determine E, other parameters has to be given. But in a regular problem, you have the mass of you have 2 masses known, right? You have initial velocities for 1 and 2 known, and you have coefficient of restitution between the 2 objects known. And if you know all of this, you can solve V1 prime and V2 prime using this equation and this equation. Any question? Are we good? Okay. Let's see what comes next. This is interesting. I think this is cobalt and this is copper. And the cobalt and copper have this interesting electromagnetic properties that when this moves, there's a strong magnetic forces created that dampens the motion of this. I don't know how easy it is to see this video, but it's almost like you hit a snowball to the wall. When this cobalt mass swings here, reaches this copper wall, let's call it that way, it stops immediately, it doesn't bounce back. You see? I don't know how it's visible. It comes and doesn't move back. This is coefficient of restitution of 0, you see? So it's not even physical contact, but that's how 0 coefficient of restitution look like. Let's do one example and then come back here. We have 3 balls. They all have the same mass. Ball A has a speed of V. B and C sitting here with 0 velocity. Coefficient of restitution between all of them is E. And it says neglect the size of each ball. Every time it says neglect the size, that means we are analyzing them like particles. Okay. So what happens is this: A comes and hits B. Based on the impact between A and B, B gains some velocity, right? Even before it moves, it has an original velocity after impact. And then it immediately hits C, and there's going to be impact between B and C, and then C moves with another velocity. So technically, you have an impact between A and B, and then you have an impact between B and C. Does that make sense? Okay. Let's solve this problem, see how it works. Switch to the screen. So this is the ground. You have ball A, then you have ball B, and you have ball C. They all have the same mass, which makes them easier to analyze. Oops. A, B, C. This has initial velocity of V. So MA equals MB equals MC, and you just call it M. E is known. VA is known. Of course, they're parametric, but we know them. Now, if I want to solve this, as I said, there are two sets of impact happening. First, impact between A and B. The equation we have, conservation of linear momentum. When A hits B, again, the forces acting between them is internal force, anti-action, reaction. They cancel out each other. So we're going to get MA VA plus MB VB equals MA V prime A plus MB V prime B. So we have two unknowns of V prime A and V prime B. Therefore, we need the second equation, and as I mentioned, the second equation is the coefficient of restitution, VB prime minus VA prime divided by VA minus VB. And I'm going to redraw them here, A and B. So during the impact, this is A, and this is B. Remember, A and B apply forces on one another, but these forces are equal and opposite. So when you combine them as a system, summation of forces will be 0, so summation of impulses will be 0, and that's why we can use this equation. Okay? Now, because the masses are the same, it makes life easier. I'm going to cancel out this all m values, equation 1, equation 2. So equation 1, and remember B and C are at rest. So practically VB, initial velocity of B, is also 0. So what remains here from 1 is simply VA is VA prime plus VB prime. And from the second equation, E is going to be VB prime minus VA prime divided by VA. And VA, we call it just V, I guess, right? Initial velocity of A, we called it V, so let's just put it that way. So if that's the case, I'm going to replace this with V. And here we're going to get V minus initial velocity of B is 0. So these are the two equations you get. If I simplify them, I'm going to get from the equation 2 that E times V equals VB prime minus VA prime. So we have two equations. V is equal to VA prime plus VB prime, and EV equals VB prime minus VA prime. We simply need to solve these problems, right? One way is to do it. I'm just going to pause here so you guys can write it down. Okay. Now, one way to do it is if I add the two sides of equation, I add this and this together, I get rid of VA, and I add this and this. So if you do that, you're going to get V plus EV equals 2 VB prime. Because when I add them, this negative and this positive cancel out each other. And then from here, you're going to get VB prime is V divided by 2, 1 plus E. That is how much the velocity of B is after the impact. If the masses are the same and one object is at rest, you can always use this because this is general. But if B had its own velocity, the story would have been different. Any question? Looks easy, right? Yeah, you have two equations. This is, and let me put it this way. In the previous chapters, like chapter 12, mainly 12, sometimes 13 and 14, you had problems that were tricky, right? If you don't know how to start, you cannot solve it. Impact problems like this, many of them are straightforward. You just use technically the two equations, conservation of linear momentum and coefficient of restitution. Now, the masses are the same. We cancel out it could be different. 1 pound, 2 pound, 2 kilogram, 5 kilogram, doesn't matter, right? So technically, two equations, two unknowns, you solve it. Now, if we go to the second part, which is the impact between B and C. B and C. Remember, B had no velocity, but after A hits B, now the velocity of B is this much. So practically, you have almost identical problem compared to the first one. Now, here's B. And then here is C. Initial velocity of B, which is, we call it V prime because it was prime, is V over 2, 1 plus E, and VC prime, which is initial velocity of C0. Now, after impact, B is going to have VB double prime, and C is going to have VC double prime. Because I use no prime and prime for the first one, I keep going that like the second prime. You can call them anything, VB1, VB2, VC1, VC2, doesn't matter, right? Just these are before impact. And these are after impact. Okay. Again, the impact of two objects, you know the masses, you know the initial velocities. Two simple equations, right? MB VB prime plus MC VC prime is equal to MB VB double prime, which is after the second impact, plus MC VC double prime. One equation gives you two unknowns. Then you need the second equation, which is going to be coefficient of restitution E is VC double prime minus VB double prime, relative velocity after impact, relative velocity before impact. Identical equations, you go from there, right? And again, you can cancel out the masses. Initial velocity for C is 0. And if you simplify that equation 1, equation 2, then 1 gives you VB prime equals VB double prime plus VC double prime. And second equation gives you E VB prime equals VC double prime. I'm just repeating the same exact equation, same exact step, because the situation is the same. Then again, you can add them together. Then you're going to get E times, VB prime times 1 plus E equals 2 VC double prime. And VC double prime is going to be VB prime 2, 1 plus E. And I can substitute this value here and get the VC double prime is equal to V2, 1 plus E, which is this guy, times 1 plus E, which gives you V by 2, 1 plus E squared. Make sense? Now you may realize that if C was supposed to hit another ball, D, the velocity of D would have been just this cube. And as you go forward, you just get 1 plus E to the power.
Shouldn't that be to the fourth? V over 4.
No. Let me see. V2. Yes, thank you. So you know what? I'm just going to put it here. I'm going to put the 2 here. So this makes life easier so we don't make mistakes. We can write it this way. V times 1 plus E over 2 all squared. And here I can write as V1 plus E over 2. So I'll put the 2 here. Yeah, thank you. So you get that. And if there was another ball, like if we had another ball here, like ball D, right? And I want to calculate velocity of D. So VD, like triple prime, which is the velocity of the DF, there's going to be V1 plus E over 2 cube and so on. Okay. Any question? Now let's go back to the slides and continue with the last part of this thing. In oblique impact, there's a little bit more to do. The overall concept is the same. Do you guys want like a couple of minutes of break? Okay. It is 12:01. Let's come back. 11:01. Let's come back 11:05. So for the oblique impact, as you see, this is the line of impact. They use T and N like normal and tangential because this is normal to the surface. I mean, the notation doesn't matter. You can use anything. And this is the plane of, sorry, this is the line of impact. And this is the plane of impact. The objects come with velocity θ1 and θ2, whatever they could be, and leave with different angles. Again, you know the masses M1, M2, you know the initial velocities. We are looking for the final velocity and possibly find out angles because this is not one-dimensional. You have to find the direction of velocity after. So you may realize that I need V1 prime, V2 prime, θ1 prime, θ2 prime. So I need 4 unknowns. Now, if we look at here, during the, I want you guys to pay attention to this part because this is important, okay? During the impact, they come with different angle, but when they touch each other, they only create force in N direction. They cannot create horizontal force because they're not sliding on one another, right? They come and go, so the forces are perpendicular to those contact surfaces, right? Which means you only have forces in N direction. Now, this is my question to you guys. A particle comes here, hits this other object and goes back. There's no force happening or creating in T direction, right? If there's no force is in T direction, how much is the impulses in T direction for single object? Someone say something, right? In T direction, let's say let's call it red and blue. When the red ball hits the blue balls, you have impulsive forces in N direction. There's no force in T direction. What happens then? Remember, linear momentum was vector, right? You guys remember? Do you guys hear me? I think I was kind of, the signal was lost for a second. Do you guys hear me now? Okay. So the first thing is, as I said, we have 4 unknowns, either normal tangential component of velocity or velocity and the angle, which is the same. You can get one from another, right? Now, because the forces are in N direction, object red M1 doesn't feel or doesn't sense any force in T direction. If there's no force or impulse in T direction, what happens to its linear momentum in T direction? Does it change? Remember the principle of impulse and momentum? The summation of forces that create impulse, summation of impulses in one direction changes the linear momentum in that direction, right? It's a vector equation. You can go T, N, X, Y, whatever. there's no force in t direction, which means the linear momentum of object 1 is not going to change in t direction. And same goes with M2. The linear momentum of 2 in t direction is not going to change because there's no force applied to the blue ball in t direction. Is that clear? So each of them will maintain its linear momentum in tangential direction. In the normal direction, you have these forces, so you cannot separate them. It is similar to the central impact. There are forces in this direction, and the linear momentum in that direction will change for each of them. But if we consider the two together, we get rid of this. So in normal direction, it's like central impact, linear momentum of 1, linear momentum of 2 in n direction before impact is same as linear momentum of 1 and linear momentum of 2 after impact. Why? Because I have these forces, I want to get rid of it. I consider them together. But as I said, in t direction, there's no force, so 1 maintain its tangential momentum, and 2 also maintains its tangential momentum. Does that make sense? So where you have forces, I don't know if you can see my hands, where you have forces, you combine them together. So you create equation 1. And if you do that, F and minus F cancel out each other because this is my system. No external impulses, initial linear momentum, final linear momentum, the same. In tangential direction, if I get the tangential component of velocity, then there's no force. So 1 maintains its tangential momentum and 2 maintains its tangential momentum. So practically, we created 3 equations, all based on conservation. We have 4 unknowns and we need 1 more equation. We created 3 equations based on conservation of linear momentum. Where the 4th equation come from? Cristobal, any suggestion?
Is it from that ratio?
Ratio what?
E.
Yeah, coefficient of restitution. Remember, this is a still impact. So the nature of the impact is affected by the physics of the 2 objects. So the 4th one comes from coefficient of restitution, but which velocities? The velocities approaching and separating. So technically, you're going to get the normal component of velocities for E. This is the approaching velocity, the denominator. The approaching velocity before impact, how they come close to one another, and the separation velocity after impact. 4 equations, 4 unknowns, you can solve it. Right? So the difference here with direct impact is that because you have angles, you create 4 unknowns, you need 4 equations. 1 is similar to the direct impact in approaching direction, which is n. The whole system maintains its momentum. In tangential direction, when there's no force, each of them maintains its linear momentum and also the coefficient of restitution. Does that make sense? Any question? Okay, let's do one example. Here, you have 2 disks, A and B, Each of them has a weight of 2 pounds. So their weight is similar, which means their masses are similar. And each of them has the velocity as shown, 4 meters going down, 3 meters going to the right. The coefficient of restitution is 0.5, and the plane of impact is given. Remember, for some reason, they show X and Y, but X and Y doesn't mean anything, okay? You have to get plane of impact and line of impact and divide these velocities into those directions, okay? I'm going to switch to the tablet. Give you like a few seconds to maybe draw this. This is technically the problem. The coefficient of restitution is given as 0.5. Weight of A and weight of B are 2 pounds and are the same. You may realize that if the masses are the same, they cancel out each other. You even don't need the mass, but at least it tells you they are the same. So I don't know if it's visible. This purple, this is your N direction, and the green is your T direction. Okay. That is how it looks like. I can fill these two with their own colors to see how it look like. So anything for B, I'm going to write it with blue. Anything for A, I'm going to write it with red so you can distinguish between them. This is B and this is A. Okay. I don't like X and Y here, so let's just remove X and Y, okay? Because X and Y don't do anything. I put it because it wasn't the problem, but because it kind of makes a little messed up the whole thing. So I'm going to take this out. I'm going to take this out. This is technically what you have, okay? Let me just keep it somewhere else in case we need it. I'm gonna put it this. You know what? Just let this. Yeah. Okay, so we need to divide the velocity components into N and T directions. So to do that, and let me also get rid of these things. So this is VA, and VA is 4 feet per second. This is VB, and VB is 3 feet per second. So I try to keep this as clean as I can, so when we do the velocity component, it looks nice. I'm going to divide B into N and T components, right? This is not the nicest one. We may not have, we don't have to make it as beautiful. So let's just do it this quickly. And then for the VA, so this is VAT, this is VAN, this is VBN and VBT. And remember the angles, this, if we call this theta, is 345. So remember, if this is theta, I am going to use green for the angle. So this is going to be theta, and then this is going to be theta. Okay. So let's go with A first. So VA or VAT, which is this component, is going to be VA sine theta. VAN is going to be VA cosine theta. If you substitute the values, because remember, sine theta is 0.6, cosine theta is 0.8. If you do that, 0.6 times 4 is going to give you 2.4 feet per second. And 0.8 times 4, 3.2 feet per second. And remember, the directions are this way and this way. This is a vector analysis, so you have to have a positive direction. I'm going to consider this direction as positive and this direction as positive, because the components of velocity could be negative. Now, if I do that, let's just apply the positive negatives right here. Apparently, VAN is in negative direction. So I'm just going to fix it here. And VAT is positive. Any question up to here? I just divided the components of velocity into N and T for A. And I'm going to do the same for B. VBT is going to be VB cosine theta, which is 2.4 feet per second. And VBN is VB sine theta. Both of them are positive. Any question? Is it good? Now that I have divided my velocities into N and T components, I'm going to go and write down the equations of motion. Or, well, the impact equation. The first equation was conservation of linear momentum in N directions. So you're going to get MA VAN plus MB VBN is equal to MA VA prime N plus MB VB prime N. As you see, there's no kind of trick or creativity required here. You just get the equations, write it down, and go forward. Equation 2, in tangential, A maintains its momentum. And for B, the same. And the last equation is coefficient of restitution. Remember, there's no preference to write B minus N or N minus B in coefficient of restitution. You just need to remember if this is B minus A in the denominator, A minus B. And that takes care of everything, right? I could write A prime minus B prime, but here B minus A, which is technically this, it's like you're multiplying numerator and denominator by -1, so no big deal. Any question about this up to here? I technically got my velocity components for A and B, and now I have the 4 equations that there were in the notes, nothing new. Because the problem says both have the same weight, which means they have the same mass, we can cancel out this thing. Here, definitely we can cancel out, right? So from this part is easy. So I'm going to go with their own color again. VA prime T is equal to VA T, which is 2.4 feet per second. And VB prime T equals VBT, which is 2.4 feet per second. So 2 of the unknowns, I found them. Okay. Any questions so far? Are you guys following or you're falling behind? Am I going too fast? That's good. Okay. Now, equation 1. On the left side, you have VAN, VA prime N, it simplifies like this. VAN plus VBN equals VN prime N, VB prime N. And equation number 4, you get your coefficient of restitution as VB prime N, VB N, VA prime N, VA N. 2 equations, 2 unknowns, right? I'm going to go with 4. Let's just substitute the values here one more step because we have the numbers. In the denominator, VAN, we have it here minus 3.2. VBN 1.8, you get this. So technically, you're going to get this becomes -5, which means I'm going to get -5 E is equal to VB prime N minus VA prime N. And equation 1, let's just substitute the numbers for that one too. On the left-hand side, VAN, which is minus 3.2 plus 1.8 equals VA prime N plus VB prime N. And here you get minus 1.4 equals so this is one equation, equation 1, equation 2, you solve it, you get VA prime N and VB prime N. I'm going to give you 2 minutes to solve this, okay? And everybody please do it. So I don't have the answer. This is not from the part of solution manual that they have the answer. And I think we can even substitute E here because E is given. Let me know if you guys get the same numbers. I technically added this equation to this equation.
I got the same numbers.
And if you look here, I'll let you know to finish this and I'm going to show you the thing.
Why did you add the two equations together instead of just substituting one in for the other?
You can do it that way because you see, I'm going to rewrite this back side by side to see what happens. The equation 1 is minus 2.5 equals VB prime N minus VA prime N. Equation number 4, that was 4. The other one is minus 1.4 is equal to VB prime n plus VA prime n, right? Who asked the question? Aaron, was
Me.
you? Okay, look at here. If I add the two sides together, because this is negative, this is positive, they cancel out each other. Look at here. You see, negative, they cancel out each other.
Okay.
It's easier. I prefer this way. You can do that the other way too. For example, if you calculate like VA prime n from here, you're going to get VB prime n plus 2.5, then substitute here. It's just one more step. When the coefficient of the unknowns is 1 or same, whatever it is, and the signs are negative, positive, you can add, subtract the two equations, get rid of one of them. That makes sense?
Yeah.
Any other question? Now, I'm going to go back to the graph. You see, the final velocity, the t direction is this guy. Oops. For the A is going to be repeated exactly, right? And for the B is going to be that guy. In n direction, you get positive velocity for A, which means you're going to have something like this. And you're going to have negative velocity for B, which means you're going to get something like that, which means they're going to bounce back like that. This is VA prime, and this is VB prime. And physically, it makes sense, right? They come like this. It comes like this, and it goes like that. And the blue comes like this and goes like that. And the numbers kind of support the physics. Any question? Did I do anything kind of novel or creative or, crazy here? Sometimes there's a trick in the problem. If you do not understand what the trick is, you can't even solve it. The good thing is this problem don't have that. You practically have 4 equations. 1, 2, 3, 4. You write them, you find the components, you substitute. It's a little lengthy, but you should be able to do something like this in 20 minutes. Because it's straightforward. Just some sine, cosine, theta, stuff like that. Any question? By the way, we're supposed to have our next quiz on Wednesday, right? Covering energy. Okay. Let's do one more problem. Go back to the slides. We did this, we did this. This is kind of similar to that one. I'm gonna go. Doesn't matter. I'm gonna do this one. Okay. And as you see in this problem, you have a 1 pound ball falling from 4 feet high. It says drop, that means the initial velocity here is 0. It hits the ground and bounces back and hits the ground at B. It says it rebounds and in half a second it strikes. So from A to B, it takes half a second. You want to get the coefficient of restitution and also the distance D. And this has a little bit of energy in it. It has a little bit of kinematics in it. So it's kind of a nice problem. So the ball falls from 4 feet. And hits the ground at A, then bounces and hits the ground again at B. The slope is 3, 4, 5. This is like how you can experimentally determine coefficient of restitution. Any question about the definition of the problem? So if I share the screen on the tablet, we are this is how the problem looked like, right? Let's just call it like 3 different position, like 1, 2, but technically 2 is 2 position, before impact, after impact, and then 4. Do you guys follow? When the ball hits the ground just before impact, it has some certain properties, velocity, everything, right? And then hits the ground and bounces back just after impact, it has different properties. So I separate before and after. 2 before impact, 3 after impact. Okay. 1 is stationary at top and 4 goes down. Now, if we analyze this, we have to go step by step. 1 to 2, then 2 to 3, then 3 to 4. What happens between 1 to 2? Free fall, right? No external forces, no nothing. We can use conservation of energy. T1 plus V1 equals T2 plus V2. T1 is 0. If I get my Y here, then V2 also will be 0 because at the end there's no elevation. So technically you're going to get mgh equals half mv2 squared because it's position 2, which means your V2 is going to be the square root of 2gh. And if you calculate this, it's going to be 16.05 feet per second. So from 1 to 2 was easy. Okay. Any question about this step 1 to 2? What happens from 2 to 3? Let's look at it from a little larger. I know we are like at 11:45. Give me 5 more minutes. You guys owe me almost 10 minutes, so we're going to stop it. I'm going to continue this later, okay? Let's say, oops. The ball comes with this angle and bounces with another angle. It's like V2, this is V3, right? You have N direction and you have T direction, right? It's almost identical to the previous problem. You're going to get N and T component of velocity before and then N and T component of velocity after, right? One of the objects is the wall. So here, let's just talk about this is like oblique impact. Ball is one object. What is the other object? What the ball hits and bounces back from?
The plane.
The plane, the ground, technically ground, right? So ground is the other object. How much is the velocity of ground before after? So V ground is 0 before and after. And the mass of ground is technically the whole earth is infinity. So technically you get rid of some equation, right? If I write M2 or M ball V2 normal plus M ground V ground normal equals M ball V3 normal plus M ground V ground prime normal. Remember, the V is 0, but this is infinity almost, right? So technically, you cannot use this equation when ground is involved. You guys follow? Because you don't have the mass of the ground, but the velocity is 0. So it's kind of like 0 times infinity, which is unknown. So we're not going to use this. The good point is ground has always 0 velocity after, so we lose some of the unknowns too. So that's okay. Then you're going to have the other equation. This is equation 1. Equation 2 is going to be M ball V2 tangential equals M ball V3 tangential before after. You can use this, right? And for the normal, you can just simply use E is V3 normal minus V ground divided by V ground minus V2 normal before after, right? Technically, you have 2 equations to solve for 2 unknowns, V3 normal, V3 tangential. Ground has 0 velocity before after. So you lose one equation and also you lose an unknown. So that's how you do it. Okay? Any question about this? So remember, anytime ground is one object, it has 0 velocity before after. So it doesn't create extra unknown. And you may lose one equation, which is fine because you also lose unknowns, and that still balances the whole thing. Right? Is it good for everyone? I'm going to stop this here. And on Wednesday, we're going to continue, finish this. Okay? So you're exposed to multiple problems. Meanwhile, I'm going to post the homework problems for chapter 15, and you can try some of them. Okay? Any question? Okay, thank you very much. And I see you guys on Wednesday. Again, please get in the room maybe 3-4 minutes early. Same format. I'm going to post a problem. It's going to appear at 10 sharp with the link. You solve it. And please go and download that CAM scanner. They don't give me any commission for advertisement, but that CAM scanner is free and it has a good quality. I've been using it for many years. The only thing is if you pay extra, they don't put the CAM scanner at the bottom. If you don't pay it and it's free, they just put their logo at the bottom, which is, I mean, who cares, right? But it cleans your page and you can create a PDF and it makes life easier. Okay? Did you guys enjoy the lecture? Okay, thank you very much and see you on Wednesday. Have a good rest of your day. Bye.